What's up, everybody? So yesterday in class, we had started this Jamboard about solving trig equations. So task one was over and over again, and we were trying to come up with basically solutions to this equation, sine of x equals 1/2. We were looking at that a few different ways, and I felt like I kind of explained it poorly, and I noticed that there were a lot of difficulties with answering some of these questions. So I wanted to clear it up. That way you can proceed to some of the other problems and kind of get this idea down. And that's what you'll be working on today in class. So just to look at a few things. Firstly, question A wants us to use the unit circle to solve the equation for x. So we're going to take a look at our unit circle. What we want to know is for what values of x will sine of x equal 1/2. So we can look at the unit circle. What we know is that our x values and our y values on the unit circle each tell us one of our trig functions. The x values, of course, are cosine functions. We know this. So cosine of normally theta, that's the angle. We're using x right now, but I'll write theta here, comma sine of theta. So the x value is cosine, the y value is sine. So we look at this unit circle, we want to know for which angles will sine be equal to 1/2. So I see y values of 1/2 in two places. We got one right here. So that means that this angle, that is one of our solutions. That angle is pi/6. So we can write that in. X equals pi/6 is true. Why? Because, well, sine of pi/6 is 1/2. When we evaluate this function, sine of pi/6 is equal to 1/2, according to the unit circle. Same logic applies. We find another angle on the unit circle for which the sine value is 1/2. We can go around the unit circle until we hit this point. And you can clearly see sine is 1/2 right here. And that angle is 5 pi/6 radians. Therefore, we have a second solution according to the unit circle. X is equal to 5 pi/6 would work. You can write that in the function itself. Sine when the input is 5 pi/6 will be equal to 1/2. Excuse my handwriting. All right, so that's revealed two of our solutions. Logically, though, according to the unit circle, we know that we could keep going around the unit circle and hit those angles again. We could get back to this point if we completed one trip and then kept going, and we can get back here. Or we could go the other way, clockwise around the unit circle and hit those points. So we should know that there are more solutions than the two that we just described. This might be more easily explained if we look at a graph. So let's hit up Desmos. If we graph sine, we'll just graph it as y equals sine of x. We want to know when it equals 1/2. So I could zoom in and I could start trying to find 1/2 as an output, but it's kind of hard. Notice how I'm having so much trouble finding a y value of exactly 0.5. I get close, but it's difficult. It's easy if we just plug in 1/2 here. Graph a horizontal line, 1/2. So now we know that y is equal to sine of x and y is equal to 1/2. So sine of x is equal to 1/2. That's the equation we're trying to solve. We can click on any points where we have intersections, and that will tell us the solution. This works for any function. If I have any function, I want to know what it's equal to, I want to solve it, I could use a graph. So here we have pi/6, outputs 0.5, 5 pi/6, the two that we had. But as we keep going around the unit circle, we get back to those values at 13 pi over 6, at 17 pi over 6, and so on. So we have a bunch of different solutions here. I'm going to snip this and put it onto the Jamboard. Just these solutions that I can see right now. About 6 of them should be good enough for the moment. Of course, there are more than this. We'll touch on that in a second. So just for the moment, let's put this graph up here. That way we can reference it as needed. All right, so we can see more of the solutions. Let's write those in. Of course, we have pi over 6 and 5 pi over 6. When we have multiple solutions like this, we can write it as a list. We know that x will be equal to the list of numbers that includes pi over 6, 5 pi over 6, and we can keep going, 7 pi over 6. Sorry, not 7 pi over 6. What am I talking about? The next one up here is 13 pi over 6. And then we had 17 pi over 6. (25 pi over 6). That's a 5, not a 3. And we had 29 pi over 6. And I think we were starting to notice a pattern in class of what's happening here. Just based off the numbers, it seems like it goes 1 pi over 6 to 5 pi over 6. So we add by 4. 5 pi over 6 to 13 pi over 6. We added 8. But that pattern is not really sufficient for what we want. We want basically an expression that will describe this. We're going to talk about that in a moment. But this is the list of numbers that we have. Now C is asking us, well, how many solutions does the equation have? Well, there are infinitely many. We're never going to run out of solutions here. There will be an infinite number of solutions to this question, or to this equation, sine of x equals 1/2. No matter what direction I go on the graph, we can see that there are an infinite number. If I kept going to the left, I'd have an infinite number of negative solutions too. This graph never ends. All right, but question D. It's asking us, is it necessary to have a way to express all of the solutions to the equation? So we want to know a multiple of what value can be added or subtracted from the solutions in part A to get all of the other solutions. Why does this value work? We want to be prepared to share our answer in front of the class, but let's just talk about it right now. So our solutions here were pi over 6 and 5 pi over 6. And we want to know what value can be added or subtracted from all of the solutions to get the next ones. So our first one is pi over 6. It's our first solution. We want to know what we can add to this to get the next solution. Let's look back at the unit circle. We have our first solution at pi over 6, which is right here. So it's this angle right here. Well, what can we add to pi over 6 to get the next solution? Well, what angle can we add? We can add another trip around the circle. This full trip around the circle from pi over 6, well, that whole angle is 2 pi. 2 pi radians, whereas this original angle was just pi over 6. So literally the only thing that I've done is taken pi over 6 and I added 2 pi more radians to get back to this place where 1/2 would be. So how can I express that? It would be 2 pi over 6 plus, or sorry, not 2 pi over 6, but pi over 6 plus 2 pi. Because we took another trip around the unit circle. I could do that again if I added another trip around the unit circle. Now I've gone around the unit circle from pi over 6 another time. So it's like I'm adding 2 pi over 6 again. That would give us the third solution. So we'd just keep adding 2 pi over 6. Sorry, not 2 pi over 6, but 2 pi to get each next solution. We could do the math to find the solutions, but I think we're starting to get the point. If I were to do this another time, I would add 2 pi again. And the same logic applies to our other solution. X equals 5 pi over 6. I'll show one graphically on the unit circle. Here's what we have here real quick. All right, so if we had the angle of 5 pi over 6, that's what we started with, takes us directly to here. That's our first solution based off 5 pi over 6. But from here, we can go around the unit circle one full rotation, which is another 2 pi radians. So we have this 5 pi over 6 plus 2 pi. So 5 pi over 6 plus 2 pi. That would be the next solution. And then we can go another trip around the unit circle, and we would add 2 pi again. And we can go another trip around the unit circle, and we would add 2 pi again. So we're just adding 2 pi multiple times. And this is going to continue to get every other solution. Conversely, we could go the other way. If I wanted to find the other solutions in the opposite direction, we could have gone the other way around the unit circle. So I could have gone 5 pi over 6 and then traveled around the unit circle this way. That would have been like subtracting 2 pi. So I could have, instead of adding 2 pi, I could have been subtracting 2 pi. So in words, to get the other solutions, we could add or subtract multiples of 2 pi, right, pi. Add or subtract multiples of 2 pi. So 1 2 pi would get me the next solution. 2 multiples of 2 pi would get me the next solution. 3 multiples of 2 pi would get me a third solution, and so on. So if we want to express these concisely meaning like in a small, neat way, if we want to express all of these solutions, we can write this expression, starting with x equals pi over 6. We're going to add 2 pi, varying numbers of times. I'm going to call that number of times k. K can be any whole number. We'll write that in a second. So if I wanted to get the first solution, pi over 6, I could make k 0. Pi over 6 plus 2 pi times 0 just means pi over 6 plus 0, which is pi over 6. I could make k 1 be pi over 6 plus 2 pi, which should be like on the unit circle. Well, actually, let's look at the graph. Be like pi over 6 plus 1 full rotation from here would take me to 13 pi over 6. or pi over 6 plus 2 full rotations from here would take me to 25 pi over 6. Same logic applies here. Or x is equal to 5 pi over 6 plus multiples of 2 pi. 2 pi times k. Whenever we have some unknown variable like this, we just need to define what it should be. So if I wrote that, I don't know what k is. We got to say what that is, where k is an integer. Remember, integers are positive or negative whole numbers. So if k was like negative 2, it would be 2 pi times negative 2, which is negative 4 pi. So that would be like starting at 5 pi over 6 and going backwards around the unit circle 2 times. And that would give us one of our negative angles. So having that as an integer means we can go any way we want. So this is a concise way to express all of the solutions here. All right, so next, you guys will do this in class today. Your task is to finish the remainder of this Jamboard. You're going to find out what about the equation cosine of x equals 1/2. So basically apply the same exact logic, but now we're trying to solve cosine. Hint, cosine is our x values. So I ultimately want you to come up with an expression, really two expressions, just like we did here, that would solve for cosine of x. You'll move on to task 2, which now wants you to think about how many solutions the equation sine of x equals 2 have. You'll explain why this makes sense with the unit circle, and I want you to visually show this makes sense with a graph. So get on Desmos and show with a graph why that's true. All right, then start thinking about task 3. For these, you need to solve the equations. One of the key things here is that it's like any other equation. The goal is to get the variable by itself on one side of the equal sign. Problem is, when we have something like this, we don't exactly have an operation yet that can cancel out cosine. But I want you to think about it just like we did in task 1 to find solutions for cosine of x. This is for all x in the domain. Same thing here for b, for all x. C and D are slightly different. They give you a domain that's restricted. So you need to find the solutions to this equation. Start by isolating sine of x for both of these equations, and then restrict the domains, and you might be able to find a better solution set. Won't be infinite solutions this time. All right, let me know if you have any questions. I'm available through Remind today or email. If you have any troubles, let me know. We'll be having a quiz eventually. I'm thinking next Wednesday will be the day that it works, even better than today. So see you guys next time. Hopefully this helps. Have a good one.